So hello, I'm Professor Vinay here from IIT Bombay. Uh,
Sir, very good morning, sir. Sir, very good morning, sir. Within a few more minutes, we
yes,
will
yes. So
start.
can you tell me a little bit about the participants? Are all from JNTU or are there people from other places too?
No, sir. Participants are also from other
From
places.
other places. Okay, okay.
Yeah, yeah.
But all are computer science teachers, is it?
The departments has diversified.
Okay,
Maybe some of the candidates from some of the participants from electrical, electronics, and mechanical as well. So
okay,
that
okay,
has been increased.
okay.
I'll let you know, sir. I'll start in a few more minutes.
Sure, sure, sure.
Thank you, sir. Very good morning to one and all. Welcome for the day two of faculty development program sponsored by Atal on blockchain technology. I feel honored to introduce our speaker, Dr. Vinay J. Ribeiro, sir, for the participants. Dr. Vinay is currently working as an associate professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Bombay. He received his BTech from IIT Madras in Electrical Engineering and his MS and PhD degrees from Rice University in the Department of Electrical and Computer Engineering. He received the Best Student Paper Award at the Internet Passive and Active Workshop 2003, a Texas Instruments Fellowship from Rice University, and also a Microsoft Outstanding Young Faculty Award from IIT Delhi. And Sir is a member of Eta Kappa Nu, the Honor Society of IEEE. His research interests are in computer and network security, belongs to blockchain, IoT security, ransomware, IoT, Internet of Things, wireless networks related to cognitive radio, LTE, Wi-Fi, L5, and indoor positioning and navigation. With this brief introduction, I request Vinay sir to take over the session.
So thank you so much. Is there a way I can share my screen?
Yes, sir.
Uh,
I'll stop my
yes,
presentation.
yes. Okay. So I will just. So let me just a second.
Yes, sir. Yes, sir.
So can you see my slide?
Yes, sir. Yes, sir. It's visible.
Okay, okay. So I think we can begin. So I'm not sure what exactly was covered yesterday, but I assume that at least Bitcoin was introduced and maybe the proof of work consensus in Bitcoin. So am I correct?
Yes, sir. Yesterday,
Okay.
the concepts of introduction to blockchain technology, model framework for designing the blockchain, cryptocurrencies, and Bitcoin, sir.
Okay, okay. So we will cover some of that a little bit today, but a few other topics also.
Yes, sir.
So I have taught the blockchain course a few times at IIT Delhi when I was there, and a couple of times here at IIT Bombay where I moved only recently. So of course it's a very hot topic, and consensus is one of the key concepts in blockchains. So just a recap of what you would have already looked at yesterday. So, as you know, blockchains use cryptographic hash functions in a number of ways. So, Satoshi Nakamoto uses hash functions in not just a single way, but multiple ways in Bitcoin. So, what is a hash function? So, essentially, a hash function takes an arbitrary input bit string, as you see over here, and it outputs a fixed length output. Okay, so for example, in SHA 256, the output is 256 bits. So what are the important properties of this hash function? So one important property is collision resistance. So it means that given the computational power we have today in the world, it's very hard to find, pretty much impossible to find two different input strings which give the same output. So we can try for million years, a billion years even, let's say with all the computational power we have today, and still with very almost zero probability, we will find two different inputs which give the same output, at least for hash functions like SHA-256. Okay. So this means that any particular input has essentially a unique output, and this output of the hash function acts like a unique ID for that input. So this is one of the properties which is used in blockchains. So what is a blockchain? Just to recap, it's just like a linked list. You have nodes in this list, and each node points to the previous node, just like in a linked list. But there's a slight difference. So in a linked list, normally you have the memory location of the previous node stored in the current one. So this first node, for example, would have the memory location of the previous one. But in blockchain, you don't store the memory location, you store the hash of the previous block. So block B1 has the hash of the block B0, B2 has the hash of B1, and so on. Okay. And the blockchain starts out with the initial block called the Genesis block that is created by whoever is starting the blockchain. And after that, blocks keep getting added one after the other to the blockchain. Okay. And you can always add a block to the end of the chain. So one important property of this blockchain is that it is tamper proof. So recall that the hash of any input bit string, the hash value is like a unique ID. You cannot find another input string to that hash function which gives the same hash value. So if somebody tries to change even a single bit in B0, anybody can clearly see that it doesn't match with the hash value stored in B1. Similarly, if you change anything in B1, it will not match with the hash stored in B2 and so on. Okay. So as long as somebody knows what is the last hash of the last block in the blockchain, the entire blockchain becomes tamper proof. Not even a single bit in the blockchain can be tampered with. So that is the strength of the blockchain, the tamper proof nature. So you cannot modify any block, you cannot replace a block in the middle of the blockchain. Unlike a linked list where you can always, replace a node in the linked list. So blockchain, you can only add blocks at the end of the chain, but once you add it, that's done. It's a done deal. You cannot change anything after that. So what is a blockchain system? Well, a blockchain system consists of, first of all, a set of consensus nodes, which I've shown here in green. So these are the nodes which maintain the blockchain. So they are the ones which run a consensus protocol to decide what is going to be the next block to be put on the blockchain. And all of them locally keep a copy of this blockchain. So in addition to the consensus nodes, so it's a distributed system. These consensus nodes could be at different locations anywhere on the internet. They could be controlled by different organizations and so on. But in addition to the consensus nodes, you have a set of users, which I've shown over here. So users are those who can make use of this blockchain. So users, what they do is they create transactions, and they broadcast these transactions. Or they would send the transaction at least to one consensus node, and the consensus node would broadcast that transaction to all other consensus nodes. And then the consensus nodes decide through some consensus protocol, they decide what is going to be the next block in the blockchain. So an example of a transaction, for example, in Bitcoin, it would be that user A pays some Bitcoin to user B, for example, and it would, of course, that particular transaction has to be appropriately signed so that only authorized persons can make these transactions. So this is at a high level what a blockchain system is. So why are blockchains getting so important? Why is there so much talk about it? And essentially, blockchain is called the Internet of Trust. What we have till today is the Internet of Communication. So internet has allowed communication at extremely high speeds. It was increasing, doubling in speed, for example, in the 90s and 2000s. And most of us have very high internet speeds today. But what the internet does not give us is trust. So suppose somebody sends you a WhatsApp, for example, is it real news or is it fake news? Right? Or suppose he tells you, I promise to pay you certain amount of money. Can you trust him? And usually the answer is no. And you would need some trusted third party of some kind to come in between, maybe the government or a bank or something, to enforce that trust. So blockchain is a technology which has inbuilt trust. So I said that all of these consensus nodes store the blockchain locally. So there is some amount of redundancy. Even if one of them fails, it's okay. You can still recover the blockchain. Also, there is transparency since everybody has it. So even other people who are not the consensus nodes can always access the blockchain to see what is in it. So there is transparency. And also there is the tamper-proof nature, which I just described, that nothing in the blockchain can be tampered with. And together, these three give us trust. And this is why blockchain becomes so important. So as you know, the applications which we have in blockchain, maybe it was discussed yesterday, for governance, e-governance, various governments have proposed use of blockchain for land records. I think Andhra Pradesh was one of the first states to propose it. Also health records and so on, electronic wills, passport, wherever you want some sort of a trust in the application, you might want to use blockchain. Okay, and of course there could be other things beside blockchain also, but blockchain could be one of the key components. So various central governments have proposed putting digital currency on their own blockchains. It is not a Bitcoin sort of blockchain, but they will have their own blockchain which has rupees or yuan or dollars or whatever. And people can immediately transact on that blockchain to each other without having to go through banks. Then there are commercial applications like supply chains. So people don't know whether the end product has parts which are coming from the original companies. Even for example, if Samsung is putting together a laptop, they are getting the smaller chips and so on from so many other countries. How does Samsung know that what chips they are getting are original? So by putting information on the blockchain as the product goes through the supply chain, it builds some confidence. Also, there are things like diamond provenance. When you get a diamond, how do you know that it is genuine or not? You can put some information on a blockchain. People have also thought of other interesting things like doing auctions, doing gaming, interbank transfers. In fact, interbank transfers across countries are taking place over the Ripple blockchain. Okay, sale of music by musicians so that they get rid of the middleman who takes most of the money usually, so they can directly sell their music to people who want to listen to it and directly get most of the profits. Of course, there are other things like verification of degrees. IITs have proposed to put their degree information online so that people cannot fake that they are from IIT or even JNTU or something like that. Somebody might put some fake information in their CV just to get a job. But by checking this blockchain, the employer can easily verify. Right? And of course, as you studied yesterday, you looked at cryptocurrencies, and there's something called initial coin offering, which was there on Ethereum, where people can sell something like shares directly on the blockchain. So blockchains can broadly be divided into two categories. One is permission blockchains. So permission blockchains, all the consensus nodes have to be some approved nodes. Not anybody can become a consensus node. Usually, like if the government, for example, is putting land records on a blockchain, the participants could be different government agencies. It could be, maybe the district magistrate has to be there, maybe some lawyers, or maybe the people who have the land record information. Different government ministries would run consensus nodes, but other people cannot run consensus nodes. Maybe they could become users, people who buy and sell land, but they would not run the consensus nodes. And popular platforms for these are Hyperledger, Quorum. Quorum is from the Ethereum group, Ethereum Consensus. There's a company called Consensus, in fact, and they are the ones spearheading Quorum, and R3 Coda. So for some time, these were the three big names. And so they have a ready-made platform which you can use. Instead of building your own blockchain, you can directly use these. I think later on in this Atal program, some people will be talking about Hyperledger and maybe Quorum also in some detail. So example of permission blockchain is of course Ripple, and consensus protocols are Raft, Paxos, PBFT. We will talk briefly about Raft and PBFT in a short while. And permission blockchains are different. Permissionless, anybody can become a consensus node. So you and I can become a consensus node. We can leave at any time. So there is that flexibility, and Bitcoin and Ethereum allow that. So of course, there are many other permissionless blockchains. Anybody can start a permissionless blockchain. And the standard consensus protocols are proof of work, which was invented by Satoshi Nakamoto, proof of stake, Algorand, and so on. So there are certain advantages and disadvantages of these. Permission blockchains, of course, you have to trust the people running the blockchain, whether it's a government authority or a bank and so on. And of course, they could set the rules. They might say that every time you do a transaction, you need to pay a certain amount to the government or whatever, right? They can set the rules. And in permissionless, of course, there is no centralized control. Anybody can participate. So it's a dream of the libertarians, so where they want less government control. And there are some advantages to that. So for example, in Bitcoin, only a certain amount of Bitcoin is created over time. Whereas and that gives people some confidence that there cannot be runaway inflation. Whereas in the current monetary system, we have national currencies. The government has authority to generate any amount of currency they want. So there is usually a lot of inflation because of this currency generation. And you don't, theoretically at least, you don't have that in something like Bitcoin. Hello? So let's go into the details of these consensus protocols. If there is any question, please feel free to stop me. So we'll start with consensus in permission blockchains. Actually, this problem has been studied for a long time, past 30 years at least, 30, 40 years. People like Leslie Lamport, Barbara Liskov, and others have done a lot of important work. They are both Turing Award winners. So why is it studied in the previous times? Well, essentially, you can use any consensus protocol which was developed for distributed systems in the past. So in these distributed systems, people assume that there are some fixed number of nodes, some n nodes, who want to maintain some database, let's say, and they want to reach consensus about what new to add to the database or what modification to make. So in our case, of course, it's a blockchain system, and so we need to decide what is going to be the next block. That is what we have to do. And the idea is usually to use some sort of a voting system. So you have n participants, and each of them might get one vote, let's say, an equal vote. Or you may want to give some nodes more importance than others. You may give some node two votes instead of one. You can do those sorts of things. And they could vote in order to decide what is going to be the next block. So the problem becomes interesting when you look at the threat model and the network model. So the threat model would say, what if some nodes are malicious, for example? What if a node says different things to different people? What if it does not follow the protocol correctly? And this maliciousness may be unintended. Maybe there is a fault in the hardware, for example, or in the software or something like that. Or it could be intended that somebody deliberately wants to do mischief, and it could become a consensus node. Okay, so the threat model would say what exactly you expect in the malicious nodes to do. Okay, and none of these threat models are perfect. Maybe in the real world, somebody comes up with an attack which is not foreseen by the threat model. But you can't help those sorts of situations, and so you want to have a general enough threat model which is somewhat realistic. So other things besides malicious nodes might fail due to some reason. So that too is put into the threat model. In the network model, we look at realistic network conditions. So usually there are TCP protocols running between nodes. Sometimes you may want to run UDP between nodes to send information to and fro. Packets can be lost and so on in between. So we have to take into account message delays. Not everybody is seeing the same message instantaneously. It takes some finite time to go across the network. Messages could be lost and so on. Also, we have to take into account the fact that these consensus nodes may not have the same clock. There may not be a global clock. There could be synchronization problems. Of course, to some extent, this is solved by the internet today, where you can synchronize your machine to an atomic clock somewhere. So there may be only millisecond delays between nodes or differences in timestamp. But still, it may happen that there is some clock drift and so on. That is usually pushed into the network model. So let's look at the first protocol, which is Raft. And so Raft was proposed in 2014. That's somewhat recently. But of course, there were things like Paxos, which were proposed earlier by Leslie Lamport and so on. So Raft looks at a situation like this. You have n nodes who have to do consensus. And the threat model says that the node can fail. So any particular node might at some point fail and just disappear from the system. So it doesn't take into account totally malicious behavior where an attacker might try to perform some attack by sending fake messages or something like that. So it's a simple enough threat model where all nodes are honest, but some of them may fail. And we expect, of course, to less than half of them totally to fail over the duration that we consider. So the idea is simple enough that you elect somebody as a leader. So initially, of course, they could have some random timers and somebody volunteers to become the leader. And so whoever is the first volunteer will become the leader. And what the leader does is that it will decide what is going to be there in the next block, and it sends out the block to everybody else. Okay, and there's no malicious behavior, so everybody accepts what the leader says. So the leader sends messages, it sends the block to all the other consensus nodes. It has the freedom to decide what transactions go into the block, and everybody accepts that block. So the problem comes in when what if the leader fails, right? So suppose the leader fails and it has sent a block only to, let's say, 2 out of the remaining 5 nodes. So I've shown the blockchain at 2 of these nodes. One of the nodes has got the block and it's added it to its chain, but the other one has not got it. So this is a tricky situation. So has the block been added or not? Because some of them have got it and some have not. So how do we resolve this situation? Does the system as a whole consider that the block has been committed or not? And so what Raft does is somewhat of an intuitive idea. So what they say is we will go by majority. So we will go by what majority has received. So in this particular case, which I have shown, three of the nodes have three of the nodes have not got this new block and two of them have got it. So according to the majority, that block should not be included. Okay, and so in this situation, we would want a new leader to be elected from among that majority. Like shown over here, I've shown one of these nodes who has not got the block has been elected as the leader. So let's look at it in a little bit more detail with this example. So the first node is the leader as I've shown here, and it has created a block shown in red. And that block has been sent. And of course, in this example that I'm showing, the majority have actually received the block. So three of the nodes have got it. And whenever the leader sends the block to anybody, on receiving the block, it has to reply to the leader. So the leader gets three acknowledgements from these nodes. And as far as the leader is concerned, it can assume that the block has been committed in this situation because majority of the nodes have replied to it. Okay, so in this situation, we look at rule number 1 shown over here, which says that only if the leader has got acknowledgement from majority, does it believe that this or does it commit this particular block. Okay. So what if after receiving these three acknowledgements, the leader fails and two other nodes have not got it? What Raft does is it starts a new leader election process. They realize that the leader has gone down because they are not getting any messages from the leader. So each of them sets a random timer, and the first one whose timer expires will volunteer to be the leader. Okay, so suppose the second node has become the leader, or it volunteers to become the leader. Now that's a problem. It's not among the majority. So somebody is elected a leader only if it gets enough votes from the other participants. Only if total votes are less than half, are more than half, is that node elected. So node 2 is going to volunteer to be the leader, but somebody will vote for it only if their own blockchain is already with that node. Only if their full blockchain is with that node. So node 2 says, I want to be the leader, and it says this is the hash value of my last block. And other nodes, these three nodes realize that, okay, they have an extra block that hash does not correspond to their last block. So they will refuse to vote for it. That node 2 will get a vote only from node 6. And that is not enough for it to become leader. So the leader election process continues until one of these three nodes volunteer, node 3 to 5, one of them volunteers to become the leader. And that will get the votes from the majority of others, and it becomes the leader. Then the leader will just tell the other nodes who don't have this block that I have received this, I am the new leader, I've got the votes, you need to accept this new block. So all of them get synchronized with the new with this red colored block, and then it proceeds. So this is Raft. It's a simplified, simple enough protocol, and it is used by different blockchains. So Hyperledger, for example, might give you an implementation of Raft. But the threat model is somewhat simplistic. What if a node does more than just being just fails? What if it is malicious in some other way? And this brings us to the Byzantine generals problem. So the Byzantine generals problem was looked at by Leslie Lamport and others who in maybe the 80s or so, I don't remember the exact date. But here is the problem. It says that you have a group of generals and they need to decide whether to attack a city or not. And the problem here is that some of them may be crooked, some of them may be malicious, and that's called the Byzantine behavior. Okay. And so what we want is that even if some of them are Byzantine, we want two requirements: that at least all honest generals must make the same decision. they must do the same thing. Of course, in our context, they would have to decide on the same blockchain. That is what we want. Uh, a second requirement that is that if the commanding general, whoever is the leader, is honest, then all other honest generals must obey him. Okay. So in this particular example that I've shown, the commanding general is malicious. So he tells two generals we must attack, and he tells two others don't attack, just to create confusion, right? He's a malicious general. So we would want the honest generals to do the same thing. They should together agree either to attack or to defend, whatever it is, they have to decide. But of course, if the commanding general is himself honest, then these honest generals should do what he tells. They should also both attack. Okay? So this is what we want to do in the Byzantine generals problem, and how to solve it. So that is the problem of the consensus protocol. And one of the early Byzantine fault tolerant algorithms was PBFT, practical Byzantine fault tolerance, proposed by Castro and Liskov, I think in the late 90s. And PBFT implementations you might find in Ripple or Hyperledger and Stellar. Stellar may use some ideas of PBFT. So what you want is that this set of consensus nodes, this distributed system, should look like a single server. A client sends a request and gets back a reply, and this whole system behaves like a single server. Okay, so suppose you send repeated requests and you get replies. The state in the system should be consistent. Suppose the client says that I want to increment a variable, and the reply says that I have incremented the variable. The next time when it reads the variable, it should read that incremented value. It should not read some other value. Okay, so this should be a consistent system. Okay, so it's like as if it's a single server, but the server has been replicated at these different nodes. So we want the safety property which says that nothing should go wrong, that when something is committed, it is actually committed, that the system doesn't renege on that commitment later on. And we also want liveness. So liveness says that when it's not just enough that something bad should not happen. Liveness says that something good should happen once in a while. That in fact the system is available to the client when it wants to do a request of any kind. The system is there to respond in a short amount of time. Okay, so the clients eventually receive replies to their requests. So PBFT makes some assumptions. The threat model says that if there are n nodes in the system, at most only 1/3 of them are Byzantine or faulty. Okay? And these faulty nodes can behave arbitrarily. They can remain quiet if they want. They can send fake messages to somebody else. Okay, they can pretend that they received some message which they didn't receive. They can do all those sorts of things. They can deliver messages out of order. So in that sense, this threat model is quite general. Okay, and in terms of network model, they assume weak synchrony. So if a message is sent out at time t, it can get delayed by time given by delay of a function delay of t, where delay of t grows not faster than t, so it's order of t. Okay, so that's that's maybe a little bit of a theoretical model, but it says that messages can't be delayed indefinitely by the attacker. So if an honest person sends out a message, the other person will receive it in order of t. He's going to get it in some amount of time. And of course, they assume that signatures cannot be forged. So how is this going to work? It's a tricky situation because you could hear conflicting messages from different people. And essentially, PBFT works on the idea of quorums. So what is a quorum? So quorum is a group of 2f plus 1 nodes. That means at least 2/3 of nodes should be in a quorum. So remember that f is roughly equal to 1/3 of the nodes. So if 2f plus 1 nodes together agree on something, they say the same thing, then it is called a quorum. So what is a good property of this quorum? So see, I said that at most only f nodes, only 1/3 of them can be Byzantine. So that means majority of nodes in a quorum has to be honest. And another important property is if you have two different quorums, then they have at least one node, one honest node, which is common to both of them. So it's quite straightforward to show this. If you take more than two-thirds of the nodes, two different sets of two-thirds of nodes, at least, of course, there's going to be a huge overlap between them. At least one-third of the nodes are going to be common to both of them. And at least one of those has to be honest, because we said we're putting a restriction that less than one-third of the nodes is Byzantine. Okay. So there's this intersection property which says that if two different quorums should have at least one common honest node, which means that you can never have two different quorums who say conflicting things. Because if you had that situation, then that honest node will also be conflicting with himself. He will be saying two different things, which is a contradiction. We said that honest nodes can only follow the protocol always. So we know that if we hear a quorum about something, that there will never be another quorum which opposes whatever the quorum has decided. And so we can use these quorums to reach consensus. If you hear from a quorum at some point, you know that in the future you will never hear another quorum which is going against it. So this is the basic idea used in PBFT. And of course, there's an availability property. You might worry, what if there is never a quorum? What if the dishonest people decide to be quiet all the time? But that's okay. If less than one-third of the nodes, so the Byzantine nodes are less than one-third, even if they keep quiet, there is still the remaining two-thirds of the nodes, the honest nodes, and they can together form a quorum. So you don't have to worry about liveness because you can always form a quorum with the honest nodes. So PBFT is a three-phase protocol. Let's say that a client is sending transactions or requests, let's say, to all these nodes. I'm just calling them replicas here because that is the term used in the PBFT paper. So these are the consensus nodes which get the transactions from the client. And let's say replica 0 is currently the leader. So it puts together these transactions in a block and sends it to the other nodes. This is called the pre-prepare phase. So this is the first phase of the consensus protocol. So for example, it sends the blocks. Now we have to worry, what if this replica is Byzantine? It could have sent different blocks to different people if it is Byzantine. Right? So how do we decide? Each of the replicas, the other replicas cannot just accept his block because so am I audible to everyone? I just wanted to check. Can somebody just...
Yes, you are audible, sir.
Okay. Yeah. Thank you. So how do we decide? It's a tricky situation. And as you can imagine, the only way to solve it, the only intuitive idea which comes is that these replicas have to talk to each other. So they have to tell each other what is the block that I got from the leader. And that is in the second phase called prepare, where each of these other nodes will tell everybody else. Each of them broadcast some information to the others in this gossip protocol. They will say that I am prepared to accept such and such a block which I got from the leader. Okay. And this is where quorums come into the picture, so if each of these replicas hears a quorum about a particular block which they are prepared to accept, it knows that there will never be another quorum to contradict that in the future. So if any node hears a quorum about a block at the prepare stage, it can lock onto that block. It can say, okay, I'm almost ready to commit this block. So why do I say almost ready to commit? The problem is that these messages could have been delayed, or some of them might have been dropped or something like that. Something might happen. So at least for temporarily, the message may be delayed. So even if some node has heard a quorum, it doesn't know that enough of other nodes have heard a quorum. Okay, some node may not get enough messages from others. So it may say that I haven't yet locked on to the message. Okay, so prepare stage is not enough to finalize the block. because even though a node has heard a quorum, it doesn't know that other nodes have heard a quorum. And that is why you have a third state over here, which is called the commit state, where they have another round of gossip where they tell each other whether they have heard of quorums in the prepare stage or not. Okay. So if a node, so if somebody has heard a quorum in the prepare stage, it's we say that it has a P certificate. Okay, that is the terminology, and they gossip about the P certificates they have heard in the commit phase. So in the commit phase, if somebody has a quorum about P certificates, then he knows that enough nodes have already locked onto that particular block, and there is no chance, you can prove that there is no chance that another block can be committed in place of this block. Okay, because enough people have locked onto that block at the prepare stage. Okay, so whoever has heard in a quorum at the commit stage for a particular block, it can actually commit. It can say that that block has been accepted by the system. I know that it is impossible, given the particular threat model and the network model, that some other block can be put instead of that block. Okay, and at this stage, whoever has got quorums can reply to the client. They can each individually reply. That is what was proposed in the paper, or we can have some way of doing this together by sending maybe one message back to the client. Okay, so this is how it works. So we have prepare phase where we get P certificates, and commit phase, which I already described, where if you get quorum about P certificates, you say that a node has a C certificate. That means it has a quorum in the commit stage, and that's when it can commit and accept the block. So it's a little bit of an involved protocol. Reading the PBFT paper actually took me several days to understand it. It's just very complicated to understand these distributed systems, to understand their proofs and so on. Those of you who have taught the uh, distributed systems or PBFT paper would I probably agree with me, right? So it's a very tricky sort of situation, very tricky situation, because the attacker can do anything, and you have to prove no matter what the attacker does under certain constraints, this sort of a gossip protocol works. So this was the state of the art. And of course, maybe I'll just quickly give this example before we go to permissionless systems. So you start out with the first node, the leader who's sending out a block in the pre-prepare phase. And in this example, I'm assuming this node is a faulty node and it just keeps quiet. I'm saying that that's all that it does. It does not send malicious messages. But what the other nodes do in the prepare phase is that they send messages to each other in the prepare second phase. They get quorums about the block, but they gossip about the quorums that they've heard in the third stage. And then once they receive quorum about the P certificates, the block is accepted. Okay. So this was sort of the state of the art. These complicated protocols like PBFT were there, or Paxos and other things were there for Byzantine consensus in permission settings. So people thought it was an impossible problem to solve consensus in a peer-to-peer setting, because first of all, you don't have a number of fixed peers. So I can't say that there are n consensus nodes, because any number can join or leave in a peer-to-peer setting, in the permissionless setting. And there is no such thing as a node identity, because anybody can create any number of identities. So for example, if I join the Bitcoin network, I can join from 10 different computers at IIT Bombay, or maybe some of you can join me at JNTU and they can also join, right? And each of us will claim to be a new person, though actually we are the same person joining from multiple machines. So there is no identity. So how do you do voting in this sort of situation? There's no fixed number of us, and we can all try to create multiple identities so that we can get more votes in the voting system and we can take over the system. Okay, so this gives us something called a Sybil attack, where people can increase their identity in arbitrary numbers and can launch an attack. So also, can we assume that these peers can be honest? So in a PBFT setting, we assumed at least two-thirds are honest. Maybe that is realistic if you have government authorities, because they are somewhat trusted and you have banks and so on. But maybe somebody hacks into a government server and maybe only one-third can be taken over. So maybe that's a reasonable model. But in a peer-to-peer setting where anybody can join, how can you say that only one-third will be honest or one-third will be dishonest? Right? So what is a good threat model? So because of this, people thought it's an impossible problem to solve. That you just cannot solve this sort of a setting. But as you saw in the previous lectures in this course, that Satoshi Nakamoto came up with a solution. So we don't know who Satoshi is. And of course, it's not a general solution you can apply in any situation. It works in the context of cryptocurrencies. It will not work in a general sort of a setting, as we'll see. And of course, I mean, it has its own limitations. It does not give us the same ideas of safety and liveness that we had in PBFT in a permission setting. In PBFT, once a block is committed, it's committed forever. That is the safety property you get. In something like Bitcoin, which is in a peer-to-peer setting, you don't have that guarantee. So just because your transaction is in a block, which gets into the blockchain, it doesn't mean it's going to be there forever. That block can be removed through some sort of an attack, as we look at some of them a little bit later. Okay, so Satoshi solved the problem in a limited setting with some relaxed rules. So Satoshi tells us that with very high probability, a block is committed. He doesn't give us 100% guarantee like in PBFT where the block will be there forever. But that high probability is good enough for most people. If I know that my transaction is going to be there with probability almost 1, or the probability of it being removed is 10 to the power of minus 9 or something, that's good enough for most people, right? So what was his idea? So he said that how do I get a vote for a person? Because I don't have identities, people can just create any number of identities. So he said 1 unit of computation is equal to 1 vote. And he said he created a puzzle so that it's impossible to fake your computation. If you solve the puzzle, you pretty much have to put in a lot of computational effort. Nobody can fake that computation. So if you want more votes, well, you put in more computation. You spend more money buying hardware or whatever to do the computation, and you can get more votes. But you cannot arbitrarily fake and create more number of votes. You actually have to invest money or hardware or something like that. Okay, so it addresses the Sybil attack. With the Sybil attack, anybody can create arbitrary identities. So what is a threat model in Nakamoto's consensus? Well, he assumed that at least rational nodes, people who are rational, have 50% of the compute power. Okay, and the Byzantine adversary has less than 50% of the computational power. So in the real world, in a peer-to-peer setting, so just excuse me, there is a lot of noise over here with a passing truck. But in a real setting, you would expect people to be rational. So what do I mean by rational? I mean, somebody who wants to maximize his profit. I would say that that person is rational. So somebody has invested a lot of money to do this, solve this computational puzzle. He wants to make profit. And I think most of the people in the world, you would say at least that they are rational. Even if they are dishonest, I mean, they may not want to follow all the rules. At least they want to make a profit, right? Good or bad. So in Nakamoto's model, at least we assume that 50% of people who have 50% of the compute power are rational. And these Byzantine adversaries are people who can do anything. They don't mind losing money also. And those people we assume are rare and they control less than 50% of the hashing power. Okay. So how does Satoshi get these rational people to behave themselves? So that is where the cryptocurrency idea comes in. And so he offers these rational nodes. He says that if you follow all the rules, you can make a lot of money in terms of cryptocurrency. So he sort of forces the honest people to, I mean, at least the rational people to behave honestly and follow the rules. Of course, nothing can be done about a Byzantine adversary who does not mind losing money. But those people you don't find among common people. Maybe you would find a Byzantine, maybe a government like the US or Chinese government who wants to bring down Bitcoin. They might be Byzantine. They might sort of invest billions of dollars in hardware just so that they can bring down Bitcoin. Okay? But ordinary people, you would expect them to be rational. So I'll just briefly go through the proof of work rules of Satoshi. So essentially, he makes use of the puzzle-friendly property of hash functions. So the puzzle is the following: you have what you take is the hash value of the previous block. This is given; you cannot change it. What I call R. And what you have to do is you have to put in a new number in the block header, which is called the nonce, which I have denoted by X. And you can change this nonce any number of times you want, but the output of this hash function, which includes this previous block's hash and also this nonce, the output of the hash has to be less than some threshold, which is decided by the blockchain rules. So you may have studied in some detail in the previous lecture how this threshold is set. There are some rules for that. It's, I mean, I won't be discussing about those rules to decide the threshold here. Okay, so maybe in the question answer session at the end of the talk, maybe if you want to, if you have some doubts, we can discuss that. But this is the puzzle that you have. So everybody has the hash value of the previous block, which was decided by consensus. Now they want to decide what is going to be the next block. So they keep changing this nonce value a lot. And this, since the threshold is quite small, they have to try millions or trillions, in fact, of these nonces in order to get an output Y, which is less than the threshold. Okay, so the hash function is such that the output is completely unpredictable. And so it's like a coin tossing experiment. You toss the coin many times by trying different values of X. And with very small probability, you get out a heads. And then somebody wins the game. Okay, and then that person who wins the game by finding a small enough hash value, he has created the next block. Okay, so in this particular example, this is the block 3, which is trying to be everybody is in fact trying to create a potential block B3. So they replace the nonce in the block, and whoever finds a nonce, okay, they're trying out many nonces. Whoever finds a nonce such the hash value of the block header is less than the threshold is a small value, he wins the game and he broadcasts it to everybody. And then they include that as the next block in their chain. Okay. So it's very straightforward. It's not complicated like PBFT where everybody gossips and they form quorums and so on. That would be impossible to do in a peer-to-peer setting because you don't even know the number of nodes. So how can you form a quorum, right? So each person locally runs this puzzle. He locally tries to solve it. Whoever solves it first will just broadcast that new block to everybody. So there is a single broadcast. There is no multiple gossiping or multiple rounds of gossiping. And the game is over and they start the new game for the next block. Okay. So whoever creates this block successfully is given some amount of Bitcoin in Nakamoto's consensus as a reward. And that actually turns out to be a crucial part of this whole system, which makes it work. So the proof of work, the good property is it is Sybil resistant. Nobody can fake their computation. There is low message complexity. There's just a single broadcast. So that means an order of n, you can say messages rather than order of n square like in PBFT. There is no single person who controls the system because every block you have a random winner. So that has some good properties because essentially with a random winner coming in, nobody can sort of control the system for a long amount of time. If somebody is able to decide what is going to be the next block, let's say for the next 100 blocks, then what he could do is he could play mischief. He can say, I refuse to accept somebody's transaction, if he knows whose transaction it is. And he can prevent liveness for that particular user or for a set of users. Whereas now you have a random winner. So an honest person, an honest user who sends out a Bitcoin transaction, he can expect his transaction to get in soon enough in one of the blocks. So liveness is also somewhat guaranteed by this system. Okay. So the system gives a reward to honest behavior, and that's very important because it forces rational miners to actually behave honestly and generate valid blocks. So let's think about it for a second. So the rule in Bitcoin is that only valid blocks should be accepted. That means the block should only contain transactions which follow all the Bitcoin rules and so on. Okay, and any block which violates any Bitcoin rule is invalid, and it is discarded by everybody else. So let's think of a small game theory type of problem. So let's say that the miner has invested a lot of money. He's paying a lot for electricity and so on. And let's say we are amortizing his fixed cost over a long period of time. And so let's say that roughly he's spending rupees C per unit time in mining. He buys a lot of hardware and so on, and he's trying to create these blocks. So it costs him some amount. Maybe it costs him 1,000 rupees a day or whatever it is, right? And let's say that this miner on average will mine M blocks per unit time. Okay, so if he has invested less money, of course, he's going to mine, or he's going to create fewer blocks per unit time. If he's invested more money, he gets more blocks per unit time, right? So sort of M, you can say, is proportional to C in general. It depends on what the electricity cost is and so on. And let's say that this miner gets R reward per block. Okay, so every time he creates a block, he gets a certain amount of Bitcoin, which you can convert into dollars or rupees or whatever, which is captured by this parameter R. So if the miner is honest, all his blocks are accepted by everybody else. So the net profit that he makes per unit time is M times R minus C. Okay, so the number of blocks he generates multiplied by the reward per block minus the cost which he's spending in electricity and so on per time. And so this is the net profit he makes per unit time. So of course the miner will continue mining only if his profit is positive. If for a long period of time he's making negative profit, he should probably go out of business. He should shut down his mining business, right? But let's assume that he's making a profit, and suppose instead of being honest, the person decides to be dishonest and he creates invalid blocks. So there is some transaction which breaks a Bitcoin rule. Maybe it tries to create a negative balance for somebody, which is not allowed, or something like that, right? Then what happens is that all other miners, everybody who's honest, will reject his block. They will throw it away. Okay. Or even if they are rational, they will reject his block because they want to make profits. And they know that if they mine on a block which is invalid, then their own blocks are also going to be rejected by other miners. So a rational miner will reject an invalid block. Okay. So this person who's trying to behave dishonestly, his net profit is going to be minus C because his block is going to be rejected. He does not get any reward. Okay. So we can use this to actually come up with a game theoretic framework to show that a rational person will always behave honestly. Okay, that you have a Nash equilibrium with honest behavior, that all honest miners will tend to this Nash equilibrium, which is honest behavior. If only a single one of them wants to be dishonest, then he's going to just lose his money. Okay? So this is very key, and it's an intuitive idea. So I think, okay, we still have some time. So this seemingly solves the problem, this proof of work. It gets rational people to behave honestly. Okay? And it all works correctly provided there is enough hashing power in the network to ensure that at least 50% are rational. So the initial days of Bitcoin, that was not true because Satoshi was the only one mining, and maybe a few of his cryptography friends like Hal Finney and so on, they were mining. But of course, Bitcoin was not known. Now, of course, Bitcoin is well known, but there is a huge amount of hashing power which is trying to solve the puzzle. and it is very difficult for somebody to get 50% of control. Only a government could do it. Okay. So there are other problems, of course, which Satoshi had anticipated, and one is with the network delay. So people are randomly sort of generating blocks, and a situation like this may happen that while everybody has this blue colored blockchain, they're trying to create a block, and let's say two people, even if they are honest miners, at roughly the same time they create a new block pointing to that block. So these are different blocks, they're slightly different. I mean, they could be very different, but even in general, you would find some difference between them. And this is a problem because you end up with a fork. So you, let's say they broadcast their blocks which they've created, and now everybody has a problem. They don't know which is the chain because there are two chains. There is a fork now. So how do you decide on this? So Satoshi said, in such a situation where you have two chains of the same length, you what each miner does is he tries to extend the chain of the block which he saw first. So in this situation, I've shown which block, which miner has, which I'm calling miner any of these consensus nodes, which miner has seen which block. He will try to create another block pointing to that. So some of the miners are trying to extend the red one, some are trying to extend the blue, I mean the green one, and one of them wins the game. Let's say that in this situation shown here at the bottom, let's say that this chain below got extended first, became the unique longest chain. Everybody got this third block before a block was generated on the upper chain. So everybody shifts to this particular block, and the top chain gets killed. It gets orphaned. Okay. So this is an issue. I mean, so this is a way of solving the problem, but of course, some blocks may get discarded from the chain, though that they are temporarily in it, which is why I said that Satoshi doesn't guarantee 100% safety, meaning that once you're blocked in, it is there forever. Because a block that is in the chain may get removed if somebody finds a chain which is even longer than it, okay, which is makes these blocks get removed. So how do you prevent these forks like this occurring? So because of network delays, you have to ensure that blocks are not generated very fast. So if the block delay is, let's say, of the order of tens of seconds, you want your the interarrival time or this puzzle being solved once of the order, at least an order of magnitude or two orders of magnitude higher than that. So Satoshi realized that it will take few tens of seconds for a block to propagate over the network, for it to be, verified by everybody and forwarded from one peer to another peer and so on in the peer-to-peer network. So he said that the interarrival time between blocks should be 10 minutes. So in Bitcoin, you have one block generated every 10 minutes. And the block size also had to be limited because a larger block takes longer time to be verified and it increases the propagation time of the block. Okay, so if instead of 1 megabyte, I had used 10 megabytes, instead of taking 10 seconds to propagate, it may take 100 seconds to propagate. Okay, just because it takes longer for the block to get verified. Okay, so in general, you don't want to have a very large block, and he decided on 1 megabyte. So that restricts the number of transactions to something like 7 transactions a second for Bitcoin, which is really no good for a global system. You want at least tens of thousands or 100,000 transactions per second, okay, for a global payment system. So Satoshi also looked at situations where you may have a malicious attacker. The person might try to do mischief. So we said a person cannot generate a block with invalid transaction, okay, because other people would reject it. But it's possible to do other types of attacks. So even if somebody is generating valid blocks, he could do other sorts of mischief. And Satoshi looked at a double spend attack as shown here. So let's say the person who's making this transaction one is also a malicious miner. So he makes this transaction. Let's say he pays somebody over the internet using Bitcoin. That person, let's say, gives him something in return. Let's say he's bought software or something. And that person gives him the software immediately as soon as this transaction gets into this block. Now, what this attacker does is he creates an alternative chain which is pointing to the parent of this block. And his game plan is that after his some time, he will release this. So he doesn't reveal this chain shown here in red. He keeps it private. And once it becomes longer than the honest chain, he releases it so that this block gets killed. So this transaction too, he either pays it to somebody else to buy something or he pays it back to himself in a different public key. He does that. And this way he keeps his money and he's able to spend it later on. And this is called a successful double spend attack, which allows him to spend the money in real life. So the Bitcoin rules prevent money being spent twice in the same blockchain. But here you don't have the same money spent in the same blockchain. You have it spent in different competing blockchains. And since this one is the longer one, he's won the game. Okay. So what the person who's selling the software has to do is he should not give the software immediately. He has to wait for this block to be deep enough. He has to wait for the block to be deep enough. So he has to wait for, let's say, 5-6 blocks to be added after this transaction. And only then he is somewhat confident that it's very difficult for an attacker to remove this block, which is deep enough in the chain. Okay, so still this particular transaction can be removed, but it will take a lot of effort for somebody in private who has less than 50% of the hashing power to generate a longer chain than this. Okay. Of course, the probability of the attacker winning depends on how much hashing power if he has. If he has only 10% of the hashing power, then the chances of his winning, creating a longer chain after the sixth block has been released, is less than 10 to the power of -3. Okay. And of course, if he has more than 10%, like 30%, then this probability increases quite a bit. Okay. But the sixth confirmation is a rule of thumb in Bitcoin, and it assumes that an attacker may have less than 10% of the hashing power. Okay. So there are various shortcomings of this proof of work solution. First of all, there is a waste of hashing power. I mean, Bitcoin uses hundreds of megawatts of power just to do hashing, and billions of dollars have been invested in just buying hardware to do this hashing. Okay, so it's a waste of money. But of course, it replaces the entire banking system. So usually the existing banking system also costs some money to make international transactions or whatever. You need a lot of, sometimes you have to pay a significant transaction fee. It takes some time to transact that money. Sometimes it may take some days too, right? And the banks, of course, also have to invest a lot in hardware and their own electricity and so on. That too costs some money. So you're replacing that banking system with something like Bitcoin, which costs a lot of money. Okay, so yes, but the question is, can we use less power or less money, and that would be better. Also, the problem of forks, that with forks, you have decreased security. So let's say that the honest people have created a blockchain which looks like this. It's not a single blockchain, but it becomes a tree just because there are lots of forks in the system, right? If you're generating blocks fast or the network delays are more, you may have this sort of a system. So your longest chain is not very long, even though there's a lot of hashing power put in. Your longest chain is only this long. And the attacker who has significantly less hashing power, he doesn't have to face any forking problem because he is generating his chain privately. There is no chance of a fork there. So he is able to easily generate a longer chain. So the honest people have generated more blocks, but those blocks are divided up across multiple chains. They're not in the same chain. So using the longest chain rule, this attacker can succeed much more easily, okay, compared to these honest people. Okay, so if there was no forking, of course, the honest people, all their blocks would be in a single chain and they would be long. So forking is a problem. So people came up with alternatives. So they said, let's not look at longest chain. Let's use something like the ghost protocol. So the Ghost protocol is like this. So how do you find the heaviest chain? So you don't look at it in terms of number of blocks. What you do is you look at the heaviest subtree. Okay, so that's what gives the acronym GHOST. It stands for the heaviest subtree. HST is the heaviest subtree. So in this particular situation, to find the heaviest chain, you start at the genesis block. Of course, genesis block has all the blocks as its in its subtree, and you look at the next block at the next level in the chain, and clearly the top one, the honest block, has 12 blocks compared to the attacker's 6. So you choose the honest block rather than the attacker's block. Even though the attacker's chain is longer in terms of number of blocks, it is not longer in terms of subtree weight. Okay, and we proceed. We find at the next level, we find the weight of that block, which is just the total number of nodes in its subtree, including itself. So we follow the one and so on. We follow them, and that gives us the chain which is accepted by everybody in the Ghost protocol. So even if the attacker releases his longer chain, he doesn't kill the honest chain because they are following the Ghost protocol rather than Satoshi's longest chain rule. So this Ghost protocol is used in something like Ethereum. Ethereum, you generate blocks every 15 seconds rather than 10 minutes like Bitcoin. But of course, Ethereum uses shorter blocks, so it doesn't cause as much forking as you would expect with a Bitcoin block. If blocks were generated every 15 seconds. But still, there are lots of forks, much more than in Bitcoin. So this, you can solve it using the Ghost protocol to find the chain, the genuine one, the heaviest one. But at the same time, it's a waste for people who have generated blocks who are not in the winning chain, because they have generated valid blocks. They are honest miners, but they don't get any reward normally, according to Satoshi, because their blocks are not in the chain. Even if they give them rewards in the chain, it's not part of the final chain. So what Ethereum says is it has a slightly different rule for rewarding blocks. It says that some of these blocks, which are called uncles, like this one, this is a potential uncle. It is the child, its parent is in the main chain. So it is a potential uncle. So similarly, this could be a potential uncle, or right, even this one could be a potential uncle, the attacker's block, right? So Ethereum allows these uncles to be given some reward. And the way it is done is that some child node, any node here in the chain, can reward the uncle. Like I'm showing here, this particular block can reward this uncle of itself, and this particular block can give some reward to this uncle, okay, and given according to some rules, so that it incentivizes people to generate blocks. People don't have to worry that if my block doesn't get into the main chain, I don't get any reward. Okay. So Ethereum, of course, changes rules a little bit. So how can we solve the issue of power? So I think we still have a few minutes, so I'll talk about some other solutions. So what does proof of work do? Well, what you do is you put the hash of the previous block, you have a nonce and a few other fields, and you take the hash of that and you try to get a solution less than the target. And you repeatedly do this, right? And that consumes a lot of energy. It has some good properties that you cannot fake your computational power, which is very good in a permissionless setting where you don't know the identities of the people. You cannot take them to court, for example, if they disobey the rules. Okay. It has good properties like a random winner, and so you're guaranteeing liveness to some extent. It gives an unambiguous way of finding the longest blockchain and so on. But we know that we use a lot of power. Okay. So the people were thinking, is there something else besides computational power which is hard for people to fake? Computational power is in the real world. It's something you're using up energy, which is a real physical quantity. And you can sort of capture that using hash value in the virtual world, sort of in the digital world. But is there a resource of some kind other than energy which cannot be faked, which the blockchain system, a permissionless blockchain system, all agrees on? Is that possible to do? And people realize that indeed that is true, because people already accept how much Bitcoin or cryptocurrency different people have on the blockchain. Okay, so it may say that user A has 100 Bitcoin or whatever, 50 Ether or something like that, whatever it is. B has, let's say, 20 Bitcoin or whatever. That they already agree to, and that's what people refer to as stake. So they know that public key correspond A's public key PKA has a certain amount of stake, which I'm going to refer to as balance of A. Similarly, B public key of B has balance B, and so on, has stake of that quantity. That is what they already agree to. Can we use this resource to do consensus? And that is called proof of stake. So people say this is, you don't have to solve a computationally heavy puzzle. You solve something else which is not computationally intensive. And solving that is a consensus protocol called proof of stake. So suppose you have a miner A who has a public key A in the blockchain, and he has so much balance of Bitcoin. Okay. What he does is he takes the hash of the previous block, puts his public key. All this information is there in the new block header, which he's trying to create. And he's allowed to put in a timestamp. So this timestamp is not an arbitrary thing like the nonce in proof of work. This timestamp has some limited range. It has to be, let's say, within 10 minutes of the current UTC time. So he's allowed only, let's say, 600 values, which he can put in currently, right? So within a millisecond or so, he can try out those values, and he can find out if he has solved this thing or not, whether indeed the hash value comes out to be less than this particular quantity shown on the right. Okay, so this target decides what the threshold is going to do. It's decided by the blockchain system. So everybody, A, B, and C, all they put their current public keys, they put in their balances. Each of them sees whether the hash value on the left is less than the right-hand side. If not, then they keep increasing this. It can try out newer values of this timestamp as time progresses. And then finally, somebody sort of wins the game. This quantity is less than what is there on the right-hand side. And then he can broadcast a block. It's accepted by everybody else. So it's not computationally intensive because this timestamp is not arbitrary. It has a particular range, and the range only increases slowly with time. Okay, so this allows us these miners to generate blocks pretty much at the same frequency as proof of work does. You can set the target so that one block is generated every 10 minutes. And people are doing it without expending a lot of energy. They only try out a few values of this timestamp. Okay? Nobody can fake this whole game because his public key and the balance is already locked in the blockchain. He cannot fake how much balance he has. Everybody has already agreed to it. Okay, so proof of stake generates blocks in a random way, just like proof of work, and it does not use any energy, pretty much zero energy. Right? And you can give people rewards for generating blocks like mining fees and so on. Right? So it seems to have solved the energy problem of proof of work. But unfortunately, there are a number of problems which are not there in proof of work. We look at a few of them. So one problem is called nothing at stake. So suppose due to some reason you have a fork, as I'm showing over here. You have a fork in the chain, and only one of the chains has to win the game. Now there's a problem. So in proof of work, how did you solve this? Well, the thing is, you had to choose. Any particular miner had to say, okay, I'm going to mine on the top chain or the bottom chain. I cannot mine on both. And because of this, it was with very high probability, it was true that one of the chains would win. Somebody would create a block on the top chain and it would win, and let's say the lower chain would get killed. Here, the problem in proof of stake is that it costs nothing to a miner to mine on both chains, which is called nothing at stake. he doesn't have to expend computational energy to extend a particular chain. So he could as well do the proof of stake on both the branches, the top and the bottom one. Because he's a greedy person. In case he generates a block on the top chain, he wants the reward there. If in case the lower one, he creates a block here, he wants money there also, right? So why try to create a block only on one of the chains? Any rational miner will try to extend both the chains. So the problem here is that the chains may extend arbitrarily for long amounts of times. You may have a fork for a long amount of time because it doesn't cost anything to mine on multiple chains. Then there is a second problem of a long range attack where let's say that the honest people are only aware of this chain shown on the top. What an attacker can do is he can go very far in the past, close to even the Genesis block, and he can start to create his private chain over here, okay, shown over here. Now, in proof of work, it is very hard for an attacker to actually create a longer chain over here because he actually has to expend energy and he has to invest in hardware. And he will, with very, very low probability, be able to generate an extremely long chain, which is longer than the honest chain. Okay, if he goes very far back in the past. But here, what the attacker does, I mean, he goes far back in the past, and let's say he has only 10% of the stake over here. So, okay, he generates a block here. Okay, I mean, he doesn't have to broadcast this block immediately. Okay, so he can try a large number of timestamps. He can look at the timestamp corresponding to this block, maybe years in the past, very quickly try out lots of timestamps till he finds one which solves a problem. He does that in real time. Okay, and he creates a large strings of blocks very fast in real time. And of course, the timestamp he puts in them corresponds to some years back. That's of course fine. It's all the blocks are private. And what he's gaining over here is that in each of these blocks, he's collecting the mining reward. So he starts out with 10%, maybe it becomes 11%, 12%, and so on. By the time he catches up with the honest chain, he has, let's say, 90% of the stake in the blockchain. Okay, just because he's getting more and more of these mining rewards. So he is able to put in timestamps now which are very close to each other. Okay, but just because he has most of the mining power in the chain. So he's able to rapidly generate these blocks by putting in timestamps which are close to each other. And by the time he comes to the present day chain, by present day blockchain, he actually is able to create a very long chain, which is longer than the honest chain, and that's when he releases it. Okay. So this sort of an attack would be impossible to do with the proof of work system because you can't fake your computing power, and even if you're getting more and more mining reward, you're not increasing your hashing power. Okay, so there's a decoupling between mining reward and stake and hashing in proof of work, and that is not true in this sort of situation. So there are various other attacks which people showed are possible in proof of stake, which is not there in proof of work. Okay, there is a bribe attack, for example, where somebody can actually announce publicly and he tells all miners that if you extend my chain over here, which has some problem with it, it's trying to do like a double spend attack, I will pay you something. So that sort of a situation is possible. And because even rational miners don't have a problem mining on multiple chains, they don't lose anything, they might accept this sort of a bribe. Okay, so people have been thinking of solutions. One of the solutions is that you have proof of stake for many of the blocks, but once in a while you have a proof of work block. So what this helps in doing is that the proof of stake type of attacks, like long range and so on, have to be restricted to this short sequence of proof of stake blocks. You can't do a very long range attack, for example, because then you would have to encounter proof of work blocks, and that would stop you. Okay, so some sort of hybrid between proof of work and proof of stake has been proposed by various people like Vitalik Buterin. Okay? But nobody has had the guts to sort of I mean, at least the big people like Bitcoin and Ethereum have not had the guts to shift completely to proof of stake. Ethereum is mulling it. They have Ethereum 2.0, which came out recently, which is proof of stake based. But the theoretical computer scientists say that we don't trust proof of stake. We know proof of work has some properties, but proof of stake, we don't know that it's going to work. Somebody might just bring down the whole system. So another issue with the proof of work and even with proof of stake is scalability. You still have a low number of transactions, like 7 transactions per second. Ethereum is also roughly of that same order, maybe 20 transactions, a little bit more maybe. So people have been thinking of solutions to scale up the system. You want 10,000 transactions or 1 lakh transactions per second, right? And there are various solutions. Some of them look at off-chain solutions like Lightning Network. We'll end with the Lightning Network. But the Lightning Network says, let's not even record our transactions on the blockchain. Let's do transactions off the chain. Okay, so it's an ingenious idea which theoretically gives us infinite scalability. And another solution is sharding, where you say that I don't have a single blockchain, I have multiple blockchains, each of which I call a shard. I have them running in parallel, so it scales up the number of transactions I have according to the number of shards. And of course, if there is a transaction which sends money from one shard to the other, I have to take care of that in some way. So that sort of makes the consensus a little bit more complex, where these different shards have to communicate with each other once in a while. So I think we are close to ending. So I think we're almost out of time. So I'll discuss with the Lightning Network in the end. So it's not exactly a consensus protocol in the traditional sense of about what to put on the blockchain. Uh, it's a sort of different solution, but still agreement is reached. It can be reached among people. I'll tell you briefly what is the idea here. So how do we spend money in real life? Think about it. So I suppose typically what I would do is I would go to an ATM or the bank. I would withdraw cash, and let's say I spend the cash in a shop and so on, right? So what does the bank record in its ledgers? It records that I have withdrawn some money from the ATM. It does not record the cash transaction which I make with the shopkeeper. Okay, the shopkeeper might come back to me and pay me with that same cash. That is allowed, right? And maybe I am giving tuition to his son, let's say. Okay, a sort of realistic situation, and he pays me some tuition fees, let's say, with that same cash I gave him. So I can buy any amount of stuff from him with the cash. He can pay me for tuition, coaching, or whatever for his son. So the cash gets exchanged between us, and all those transactions, the cash transactions, are not recorded on the bank ledger. So Lightning Network is something like that. It says that when I withdraw money from the blockchain, that I record on the blockchain. That is recorded on the Bitcoin blockchain. But when I pay somebody else and he pays me, we can do that infinite amount of times. I can pay him a little bit of Bitcoin, he pays me, and so on. And we can update the balance of what we have on our own privately without recording it on the Bitcoin blockchain. Okay, so the Lightning Network takes care of ensuring that nobody can cheat in these off-chain payments. So let's take an example, A and B. Let's say A is me and B is the shopkeeper, right? And both I withdraw 1 Bitcoin, he withdraws zero point 0.9 Bitcoin. And this is recorded as a Bitcoin transaction. It is put on the blockchain. No, none of us can argue about that, right? The Bitcoin consensus has agreed to it. Now I want to pay him some Bitcoin, let's say 0.1. So the new balances have to be updated. Mine has become 0.9, his has become 1.2. He might pay me 0.2 or 0.3, and accordingly the balances between the two of us has to be updated. Okay. So this has to be taken care of by some manner, because suppose, let's say I am dishonest person, or let's say Okay, in this particular situation, let's say that shopkeeper is dishonest, right? And actually he has zero point 0.4, but what he wants is he wants to claim that he has one Bitcoin. Okay, how are we going to prevent him from telling the rest of the Bitcoin people that he has one Bitcoin? Okay, so how this is done is with a series of smart contracts. So what I do is initially, let's say we have deposited our money in some transaction. Of course, I had zero point 0.9 in our original example. So this transaction called the funding transaction is there on the blockchain. And it says that if at all this money has to be spent, both of us have to create a transaction in order to spend it. Unless both of us agree, we cannot spend it. Okay, so initially we agreed to spend, let's say, 1 and zero point 0.9. So because that was the initial amount, at least in the example I had earlier. Here it would be 1 and 1. We agreed to spend that amount. But as the balances change between us, we have to agree on newer transactions to spend that output. So the final transaction which spends, or the latest one, should say that I have 1.5 and the shopkeeper, has only zero point 0.4, right? So this has to be done in a clever way so that old transactions, older agreements which we had made, none of those were broadcast to the blockchain. They were just kept privately. uh, I have to create this new one in such a way that the shopkeeper cannot broadcast an old one to pay himself one Bitcoin. So this is done in a clever way that if anybody tries to broadcast an old agreement which we made privately, he will be penalized heavily. Okay, and the other person gets all the money. Okay, so somehow you have to agree on what is the latest transaction and so on, which is what the Lightning Network rules take care of. So what I've shown here is a single payment channel between two people, and they can repeatedly pay each other any amount of money, right? Without actually recording these all on the blockchain. Finally, if anybody wants to quit and take his money, he's sort of had enough with this single payment channel. Suppose I want to use my 1.5 pay to somebody else. What I will do is I will broadcast this final agreement we have made. It goes as another transaction on the blockchain. And after that, I'm free to use my 1.5 Bitcoin in any way. And the shopkeeper can also use his zero point 0.4 Bitcoin in any way. But until one of us sends this final agreement we have made, our money is locked into this payment channel. Okay, so that is one of the shortcomings of this Lightning Network. So how do people pay each other arbitrarily? And that is through multiple payment channels. So suppose A wants to pay C or D, and he does not have a payment channel with one of them. Okay, but luckily B has a payment channel with C and C has a payment channel with D. Okay, so how to do this? So the way it's done is through something called multi-hop channels. So A makes an agreement. Suppose A wants to pay 0.1 Bitcoin to D. So what he would do is he would make an agreement on his own channel to pay 0.1 to B. B has to make an agreement with C to pay 0.1. C has to make an agreement to pay 0.1 to D. It has to go on this path all the way to D. And if A pays B, then we sort of have to ensure that B pays C and C pays D, so that D gets his money. Okay, so it's a very tricky situation. And through clever smart contracts on these three different channels, you can actually enforce this by something called hash time lock contracts. So it's a very ingenious idea. And all of this is done off the Bitcoin blockchain. Okay, so initially to create channels, you have to put funding transactions, but then you make all the transactions off the chain. And only if somebody wants to quit the Lightning Network, to quit his particular payment channel, he will deposit one transaction on the Bitcoin blockchain and take his money. But these nice thing about these Lightning Network transactions are that they are instantaneous. I don't have to wait for 6 confirmations or anything, because my transaction is not going to get into the Bitcoin blockchain. It is all done off the chain. right? I can reduce the amount of transaction fees which I pay miners and so on, right? So I think we are out of time and I've reached my last slide. So if the organizer permits, we can have a few questions. And here is my email address if you want to send me any email. I've also sent the slide. I've sent my slides, a link to the slides to you in case you want to refer to the material later on. So thank you. We can have some questions if there is time, if time permits.
Participants, if you want to ask question, you can unmute yourself.
Hello.
Yes, yes, please go ahead.
Sir, this is Shweta Gupta. That was a wonderful presentation, very deep, informative presentation, I must say.
Thank you.
Sir, actually, I'm doing research with blockchain. Either more asking because I have a lot of doubts understand under this. So I just wanted to have your contact number. If you can please guide me for my work.
So that we can take offline. You can send me
Okay.
an email to this address. So as
Okay.
you can imagine, we have a lot of students at IIT too, right? In
Yeah,
fact,
yeah.
I'm guiding people at IIT Delhi too because I just shifted
Okay.
from there. So I have
Okay.
many students there and here. So it's a little bit difficult. So
Mm-hmm.
maybe some high level guidance I can give once in a while, but
Yeah,
but
yeah.
not hands on sort of guidance.
No, no, not
But
I don't want hands-on.
yeah, yes, but we
I
can
just want
discuss that
concept.
offline. I think if there are any questions about the material, we can take that.
Yeah, yeah. Actually, this is related to this consensus, but I need to discuss offline. I would because it will take time.
Okay, okay,
Thank you, sir. Thank you.
okay, okay. Any other question?
Sir, there is a question in chat box from Dr. Tirshala Nagasai Kumar.
Okay.
He has stated that can chains be circular, one side miner, the other side attacker?
No, so it's not like a linked list completely where you can have circular linked lists and you can where you have a front and back pointer and so on. So with at least the blockchains that I am aware of, it's just you have a single hash pointing to the previous one. So you will never have a circular circle possible. Otherwise, you would break the hashing assumption of a collision, collision resistance. You would sort of be able to break that, right? So that's not possible. It's just something which looks like a singly linked list, and you will not have anything circular. Any other question in the chat box or
No, sir,
any?
no
Yeah.
question. That's the only question. Is if any other participants want to ask, they can unmute themselves. Participants, please.
So okay,
If
there
no
are
question, we can close it now.
attendance links. Somebody, there are no questions. Can you? Okay, there are some questions. I'm just going back. Can you please explain concept of longest chain? Longest chain, briefly, it means a longest number of blocks. But Satoshi realized actually that is not a very accurate description. You actually have to look at the total proof of work in a chain to decide on what is the longest chain. So there are some rules for that. Roughly it means the longest in terms of number of blocks. And I'm just looking through any other how threshold value will be decided. That should have been discussed yesterday since you had a full talk on Bitcoin. But basically the point is that you want a block every 10 minutes. Right, and you have to decide the threshold such that on average it takes 10 minutes for somebody to solve it. So this is done in every 2 weeks. What Bitcoin does is it looks at Actually, every 2016 blocks, they look at, it should have taken 2 weeks to generate those blocks. But if it takes longer than 2 weeks or less than 2 weeks, they adjust the threshold. Just because more people may have started hashing, or some people may have withdrawn from the hashing. So roughly every 2 weeks, you update the threshold to ensure that it takes if the hashing power remains the same, it will take on average 2 weeks to generate 2016 blocks. So the question is, do we need consensus algorithm in all the implementation? No, so the question is, can I do without a consensus algorithm? So see, usually a blockchain system it's a distributed system with multiple participating entities. So if you have your own, if you have a single server maintaining its own blockchain, and it doesn't care about anything, if there is that sort of an application, then you don't need consensus. I mean, you can do whatever you want, right? But usually in the blockchain system, the strength comes from a distributed system where you have different participants, and they can all collaborate to generate transactions and blocks and so on, right? That's where the strength is. And in a distributed system with multiple parties, you need consensus. So you need a consensus algorithm. So any other questions? Uh, okay, so if there are no questions, we can, I think the organizer can take over. For implementing blockchain in my organization, yes, go ahead, Sumit Kumar. Okay, so yes, many people. So there have been pilots in India. I mean, so many like Andhra Pradesh. I think Telangana has also looked at land records in their blockchain. There was some other things like I think Punjab too had something. There was a recent news about that. So governments understand that blockchain is a powerful concept, and they have had pilots, but they have not actually. I haven't heard of even the RBI, for example, called me for some talks. They wanted to shift RTGS to blockchain, right? But again, they wanted a pilot first. Just people want to build some confidence before actually going full time into blockchain. And of course, I mean, COVID has sort of held up some of the projects, but yes, there have definitely been pilots for various things like land records. Uh, in mechanical engineering, do we need consensus? Sumit Kumar says that yes. I mean, if you have multiple participants, you need consensus. In mechanical engineering, any specific applications? Uh, I mean, I'll have to think about that. You'll have to think about like, I mean, there are things like driverless cars, for example, right? I mean, it doesn't fit exactly into mechanical engineering, but maybe mechanical engineering is part of it, right? But the idea is that you have cars, let's say, which don't have drivers driving around. And consensus is important over there, right? So let's say you have 5 cars approaching an intersection, or something like that, right? All have to agree who's going to go first, right? So in that sort of a situation, some blockchain or consensus protocols might be useful. But so you have to think, where do you require a lot of trust. So in space systems, for example, you want a lot of redundancy, because if one system fails, ISRO does this, right? Or any NASA or whatever that system. Yes, if system fails, then you don't want the rocket to crash. So you have multiple systems, and they need to have consensus, right? So usually they go with some sort of a majority rule. Whatever the majority of systems decide, that is what is done, right? So you might want to think of those sorts of systems, right? Or wherever you need some sort of trust in systems, you might want to use something like a blockchain, right? Even a mechanical system which may need some security, that an attacker might come in and do some mischief. you may want to do that, right? Or supply chain for mechanical parts definitely could use blockchain, right? So best tool for implementation of a blockchain. So I think you should wait for the presentations later today and tomorrow and so on. They will talk about Hyperledger and so on. But my students and I have tried out things like Hyperledger, Quorum, R3 Corda. Right, they are all systems being continuously evolved. They are fixing bugs or coming up with new features. So I cannot say now which is the definite best one. You should look at what are your requirements and then choose one of these. But building a blockchain from scratch is not advisable because it's a lot of effort. Satoshi was a genius; he could do it, right? If assuming Satoshi is a single person, but maybe it's Leslie Lamport, some people say, or somebody of that caliber, right, who's capable of doing something like that. But normal people, even IIT students, shouldn't try to build. I mean, anybody, no matter how smart you are, you shouldn't go just with building a blockchain yourself because there are a lot of issues to consider. So use one of the existing permission blockchains if you need it. Or if you want a permissionless system, you can go for Ethereum or Bitcoin. All the code is available for free. Scalability is a open research question. I have a paper, you can look at it, but there are lots of unsolved problems, right? So you can look at the papers, which you can look at my paper and look at the ones I've cited also, right? As a related work, that may give you some idea. Okay.
So I had a question.
Yeah. Yeah.
Like for research purpose, since we people, suppose I'm working on e-voting system. So
Okay.
like there are already secured algorithms have been proposed for implementing it. But somehow, if I I should go for the platform, the already inbuilt platform to develop that web-based voting system, or I should draw it from the scratch to present in good journals, or actually be to implemented, means to get good results.
So if you have a full implementation of an e-voting system, then you can maybe try to start with that and modify it. But if you
Mm-hmm.
only have an idea of an e-voting system published in a paper and you have to implement that idea yourself,
Mm-hmm.
you should see if there is an existing blockchain you can implement it on top of. Because
Okay.
like in the, if you're familiar with network protocol
Correct.
stack, right, you
Yeah.
have
Yeah.
various protocols at lower layers which handle
Yeah.
the complexity, and
Mm-hmm.
you can build an application on top of it.
Mm-hmm.
Like that, you have a blockchain layer, a blockchain stack, where you
Mm-hmm.
have at the lowest layer, you will have network, which includes all the networking protocols. Then you have consensus layer, right? Then you may have a scalability layer, and
Mm-hmm.
finally an application layer. So if you have an existing thing like Hyperledger, it would have taken care of the lower layers, and you
Yes.
just implement e-voting as an application on top of it.
So
That
Hyperledger would be a perfect, means it's permissionless, and we can use it.
No,
It's
Hyperledger is
permission.
you
Permission.
permissioned. Yes,
Yeah. Okay.
yes. You could use Hyperledger or Quorum or
Okay.
R3 Corda,
Okay.
and those are the three big names that people have tried out. Even people in Singapore, you can look at the UBIN project, UBIN. That is a
Yeah.
Singapore project, a Singapore government, and they
Mm.
have tried out all three. I think, in fact, they just to
Okay.
demonstrate their application.
Okay.
Yeah.
Okay. Thank you, sir. Thank you so
Okay.
much.
Okay, sir.
Okay.
Yeah, yeah. Yeah. Thank you so much, sir. On behalf of Shobha Bindu Madam, I must thank you very much for accepting our invitation. And
You're welcome.
participants are much benefited out of your content and the way you have explained the concepts related to Bitcoin and all.
Yes, yeah.
Nice session, sir. Thank you so much, sir, for giving such an informative session.
You're
Thanks for
welcome.
being part of this program. I hope our collaboration will continue for the future programs as well, sir. Thank you. Thank you so much.
Yes, sure. Thank you so much. Thank you. So I'll end the call then. Okay.
Yes, sir.
Thank you.